7/5, October 3rd. Let's just double check what this says. Yeah, so it's the same as the quiz. Yeah. Right. So those are Monday because we're going over questions today. Yeah. So.
Just checking.
Yep, that's correct. Yeah. Yes. Yeah. So the notes in D12, I had the dates a little bit off because we kind of moved from last semester. We moved a little bit of the content so that there's some more time for some other stuff. So 7/5 we pretty much did on Thursday last week. So if you look in the notes on D12, I had 2 separate days, 7/4 and then 7/5 was by itself. We pretty much did those questions on Thursday. We'll go over more of it today, though. You know, if there's anything you're not sure about, we'll go over it today. So let's start with these 3 homework questions and make sure that they make sense. And then we'll go from there. So the first one, we are trying to evaluate a composition. And the functions are inverses of each other. We have tan and inverse tan, so they're inverses of each other. Sometimes those will cancel and sometimes they won't. They will always cancel if the inverse is on the inside and the regular trig function is on the outside. Then they'll always cancel in that case. If it's the other way, inverse on the outside and regular trig function on the inside, sometimes they cancel. And the way we can tell is by looking at the angle and figuring out whether that angle is in the range of the outer function. The outer function is an angle, right? Inverse tangent's an angle. And so we have to check that angle in there and say, is that angle in the range of inverse tangent? And is it? Pi/3 is in quadrant 1. Inverse tangent is an angle on the right. Pi/3 is on the right. So in this case, it will cancel. Okay. But let's take a look at another example. If we had inverse tangent of, let me pick an angle not on the right. Let's say 5π/4. So any angle that's not on the right. There, it won't cancel. Let's take a look at a little picture just to make sure that we're sort of seeing it clearly. So 5π/4 is in what quadrant? So 5π/4, if we go over to 5π/4, 1, 2, 3, 4, 5π/4, there's the angle sitting in quadrant 3. But we know inverse tangent is an angle that sits on the right side. So in a case like this, we just go to the inside and evaluate. We're going to go start in the innermost parentheses and work our way out. So here we will get inverse tangent of tan of 5π/4. We go to 5π/4. The tangent is the slope of that terminal ray, which is 1. And then we can solve the outermost piece. Inverse tangent of 1 means angle on the right with a tangent value of 1. And what angle on the right has a tangent value of 1? Yeah, π/4, exactly. So that's how that works. Make sense, all?
Yeah.
So any questions on that when the functions are inverses of each other and how you know if they cancel or not cancel? If you don't want to get to that bigger conceptual level, you can always just start on the inside and work your way out. Getting that bigger conceptual understanding is very helpful, though. All right, another one. So this is 7/5, number 29. Or in the homework it was 9. But it comes from the book. If you go look in the textbook, it's based on problem number 29. That's the parent problem. So here we have a trigonometric equation that we're trying to solve. And our general principle is that we would like to have 0 on the right and then a factored expression on the left. That's our strategy. They've already got 0 on the right for us. So what we're going to do is factor on the left. We need to try to get a product of factors, because if we have a product of factors, we can apply the 0 product rule. A times B equals 0 means A is 0 or B is 0. So we factor out the 8 tangent of x, leaving the quantity sine x minus 1 equals 0. Now we can apply the 0 product rule. We have this factor multiplied by this factor, which means one of those factors has to be 0. So this implies that either tangent is 0, or for this to be 0, sine of x would have to be 1. So those are our two possibilities. So we're going to go to a unit circle just to get a nice image of what our solutions look like. We can use a 4-sector circle here because our places are here, tangent is 0, here, tangent is 0, there, sine is 1, and that's it. So those are the 3 locations on the circle, the 3 terminal points that correspond to solutions to those 2 equations. Any questions up to that point? Yeah?
And you can factor out the 8 tangent x without affecting that sine x at all?
Yes, because this is a product. This is 8 times sine times... let me start over. This is 8 times tangent times... You see it? Good. Yeah. All right, this... There's no, there's separation by multiplication there. So you can treat it like A times B times C.
There's like a plus there.
Then, then it'd be a little different. Or if somehow this was inside the tangent function, we wouldn't be able to peel it off. So those are our 3 representative solutions. We should know in our head that these are representative solutions. And what I mean by that is if we're at pi over 2, we also could add 2 pi or subtract 2 pi and get to another coterminal solution. So the ones that we see right there are the 3 representative ones. Those are the 3 that are in this interval right here, 0 to 2 pi. And if our angles are just x, then the angles that we see on our unit circle are going to be the answers that are between 0 and 2 pi. Last class we saw that if the angle was a multiple of x, then things were a little different. We'll do some of those too. All right, so, and on the test I'll ask you for both all solutions and the solutions that are restricted. So this is a restriction to the interval 0 to 2 pi. So I'll ask you for both. So let's answer both. So all solutions first. These 2 for tangent, that one and that one, we can get all of those in one fell swoop. We can say that, let's see, what's our angle? X. So x is equal to, if we think about this, we're going to be separating this and this angle by pi in either direction. So we could say x is equal to pi times k. K is an integer. So if k is 0, we're right there. If k is 1, we're here. If k is 2, we're here. If k is 3, we're here. If k is 4, we're there. So that k is just going to count us around between the right edge of the circle and the left edge of the circle. Or x could be pi over 2 plus 2 pi k. So 2 pi k is going to count us either clockwise or counterclockwise back to the top of the circle. So those are all solutions right there. That's it. All solutions. And then if we want just the 0 to 2 pi solutions, if we want the restricted set, it's just the ones we see. X is equal to 0, pi over 2, or pi. Those are the 3 restricted solutions. So any issue with any part of that? It looks so easy when I do it. Yeah?
If
if we had pi over 2, does that make tangent over 0?
Oh, awesome question. Awesome question. Really good question. Okay, so I had my I was looking at these little equations right here, and I wasn't looking at the big picture. Excellent question. It's true that pi over 2 plus 2 pi k satisfies that, but if we look in the big picture, the x value, if we plug in the x value, if we go, remember how when you have an equation, if you square both sides, you could introduce extraneous solutions? There is a subtlety here that's very similar to that. When we look here, we see the solution, and maybe the better expression is potential solution. And at the very end, we should go back and check to make sure that those potential solutions are really solutions. And that is true. If we plug in pi over 2 right there, we get something that's undefined. So that is actually an extraneous solution. Excellent point. Extraneous solution. So it's a potential solution because of this. But then when we go back and we check, it's actually not a solution. Thank you very much for noticing that. So those are actually not part of our final solution set. Yeah, good. Thank you. Most of the time, we don't have to go back and check. But when we are dealing with answers that are right on the axes, we need to be a little bit more careful because that's where there's undefined values. It's right on those quadrantal angles. Yeah, excellent point. That might have been what you were getting at. Yeah, really good. Okay, let's take a look at this one. So here, our general principle is the same. We want to turn this into multiplication. We want to get rid of the addition and turn it into multiplication. And if we factor 4 secant of x out of the first 2 terms, we can do a grouping type of thing. So 4 secant of x, and then I'm factoring it out of the first 2 terms. So that's cotangent x minus 1, and then plus cotangent of x minus 1 equals 0. And if I want, I could emphasize this common in algebra. We called it a binomial factor. These aren't really binomials, but 2 terms. This common 2-termed factor we see. That jumps to the front because it's common to both. So that's jumping to the front, and what's left is 4 secant x plus 1. Bless you. And that's all equal to 0. All right, so that tells us that we have 0 product rule going on now, so either the first factor is 0, so this tells us that cotangent of x is equal to 1, or secant of x is equal to minus 1/4. Let's go with the first one. Cotan x equals 1. Let's get an 8-sector circle out there. So cotangent is 1 at the same exact places that tangent is 1. Right? The reciprocal of cotan is tan, and if the reciprocal of 1 is 1, then we're good there and there. 2 places where tangent and cotangent are equal to 1. Secant of x is equal to negative 1/4. If the answer is not jumping out at you, switch it to cosine. This means cosine of x is equal to the reciprocal of that, which is negative 4. And solutions for that? None. Cotangent of x is always between negative 1 and 1. It's on the unit circle, so that definitely contributes no solutions. So our group of all solutions, we jump up here to pi over 4, so x will be pi over 4 plus, because we have a nice even space between these, pi this way, pi that way, we can just do pi k. So that will be all solutions. We don't have to worry about what we just dealt with in the last problem because there's nothing undefined in this equation. And we don't actually need to go back and plug these in and notice there's no places where there's undefined values. The only time there's ever undefined values for the trig functions is potentially at those 4 spots on the unit circle, the top and bottom or the right and left. It's the only places where there could be, where you might have to double check. And then if we restrict our solutions to the interval 0 to 2 pi, we see the two answers, pi over 4 and 5 pi over 4. So those would be our questions on that one? Does that look good? Yeah, sure.
What happened to the second cotangent? Why did it become 4
How did this appear?
Yeah.
Okay, so let's look at an algebraic example that's similar and make sure that. So we're using a technique called factoring by grouping. So if we have something like A, B plus A, and then over here we have B plus 1 equals 0. If we have something like that, what we're doing is factoring out the A from the first 2 terms, leaving B plus 1. And then over here, there's nothing to factor out, but it's helpful if you think about a 1 as being the multiplier in front, because it's really common in this situation to factor out the B plus 1 and drop the 1 and forget that it's B plus 1 multiplied by A plus 1. So that's what we're doing. So that, back in algebra, we called that a common binomial factor. So instead of factoring out just a single variable like an A, we're factoring out a sum. We're factoring out A plus, in this case, B plus 1 from both. Okay. Other ones from the homework you want to look at? We'll do it. Today we're going to do a bazillion examples. So exam Thursday, standard stuff, no graphing calculators, no phones, no note cards. And then our topics are basically all identities and then solving trig equations. Those are the topics. And as we go through today, I'll make sure I emphasize what equations you have to remember and which ones I would give to you if they were on the test. So we'll clarify exactly what formulas, what identities you need to know. And the basic rule is know the sine and cosine ones for those two. Those are the most important. Right there. Sum and difference and double angle. All right. So let's go through some of these and refresh memories. All right. So starting from the beginning, find exact value. Actually, I want to start from the end. I want to do a couple more examples of what we did at the end of Thursday. Before we start from the beginning, I want to do at least 2 examples from the end. Let's do a couple more multiple angle equations, and then we can do a couple more at the end of today, just to make sure that we get enough exposure to these. So let's look at a couple of these. So if I have tangent of 4x equals root 3. So let's solve that. So the first thing that we're going to do is identify the circle that's going to be the best way to look at our answers. And when we see a tangent value of root 3, we should be thinking 12-sector circle. And what quadrant should we be in? Definitely 1 and 3. So tangent is positive in quadrants 1 and 3. So we should be thinking about those 2 quadrants. And are we thinking about the steep terminal ray in quadrants 1 and 3 or the less steep terminal ray in quadrants 1 and 3? We're thinking of the steeper one. That one has slope root 3, and the less steep one has slope root 3 divided by 3. So a third is steep. Okay, so those are the two places. Those are our representative solutions. And the thing that's a little tricky is that these are representative solutions not for x, but for 4x. So this is telling us that 4x is equal to pi over 3 plus pi k. So you could treat it like if you wanted just the quadrant 1 solutions, you would say pi over 3 plus 2 pi k. Then you would go over here, and you would have to do 1, 2, 3, 4 pi over 3 plus 2 pi k. But when your solutions are opposite like this, opposite on the unit circle, you can do just one statement and use a pi k instead of a 2 pi k. Okay, so those are pictures for the solution to 4x. How do we get x? Divide by 4. Exactly. So when we divide by 4, we have to divide both terms on the right by 4. So this is all solutions right there. That's all. And if we want to restrict it 0 to 2 pi, we're going to get certainly pi over 12. Now normally if you have just an angle that's like x, if it's not a multiple angle, you look at your picture and you say, oh, there's two solutions between 0 and 2 pi. But if you have a multiple angle, that's not the same. You've got to do something a little different. Anyone know how many solutions we're going to have? 8. We're going to take that multiplier and multiply the number of solutions that we see. So we know we're going to get 8 solutions. How do we get them? Well, let's come down here to our k business. Let's take the pi over 4. Let's rewrite that so that it's 3 pi over 12. Because I'm trying to add pi over 12 to this. So it'd be more convenient if we had the same denominator. And when k is 1, we're going to have pi over 12 plus 3 pi over 12, which is 4 pi over 12. And that can be reduced. 4 pi over 12. Yeah, but that'll be pi over 3. So I'll put the reduction right below it. All right. So what we did was add 4 to the numerator. And that pattern will persist. So we're going to add 4 again. So we went, actually, what did we add? We added 3 to the numerator. We went from 1 pi to 4 pi, so we're adding 3. So then we're going to get 7 pi over 12, 10 pi over 12, 13 pi over 12, 16 pi over 12, 1, 2, 3, 4, 5, 6, 19 pi over 12, and 22 pi over 12. And let me just put the simplified ones right down below. There's a couple of evens where we can cancel out a 2. And then a bunch where we can't cancel out anything. Let's see, 4 goes into both of those, so we're going to get 4 pi over 3, 19 pi over 12, no simplification. This one, I think just 11 over 6. All right, so those are the restricted answers, the restricted solutions, where we're only considering angles between 0 and 2 pi. If we were to add 3 again to the numerator and get 25 pi over 12, 25 pi over 12 is more than 2 pi. We're only looking at answers between 0 and 2 pi. If we add another pi over 4, which is 3 pi over 12, if we add another one to this, we'll be too far. We'll be outside of the 2 pi end. Any questions on that? That makes sense. So a couple of really important points. This is the first thing. We have to divide by that multiplier. And then the second important thing is that we have to distribute that division. And then the third thing is that when we're looking at our 0 to 2 pi answers, we're going to have whatever the multiplier is multiplied by the number of solutions we see in the circle. All right, let's do one more of those. All right, you guys do that one. Sine of 2x equals -1. Sine 2x equals -1. And again, find all solutions, and then also find the restricted solutions to the interval 0 to 2 pi. John Paul. Anybody else not get back a test? Jacob? Gary is not here. Sine is -1 down below. Bottom of the unit circle. That's where sine is -1. So our first statement is that 2x is equal to 3 pi over 2 plus 2 pi k. Right? 2 pi k will bring us back to the bottom of the circle, either clockwise or counterclockwise. So we've solved for 2x. To solve for x, what do we do to both sides? Yeah, divide by 2. Definitely doesn't seem that hard. There's a lot of places to make little mistakes. So remember to divide the second term by 2. So 2 pi divided by 2 is pi. Don't forget that. So there's all solutions right there. So in some sense, finding all solutions is easier than finding the restricted solutions. You just have that plus pi k business. Now we actually have to think to get the restricted solutions. Yeah, I know. It's Tuesday, though. We should be able to do it. How many solutions should we see total then between 0 and 2 pi? Just 2. How many do you see? 1. You see 1, and if you double 1, you get 2. So let's see. So certainly we have 3 pi over 4. And then up here we have to add pi. So let's rewrite that as 4 pi over 4. It's a little easier to add if the denominators are the same. So we're going to get 7 pi over 4. Okay. Now if we added 4 pi over 4 to that, we would get 11 pi over 4. And isn't 11 pi over 4 greater than 2 pi? Yeah. Right? 4 goes into 11 more than twice. So we know that we've gone too far if we end up with an angle that's greater than 2 pi. Then we've gone too far. So 0 to 2 pi, solution set, just 2 angles. And those are that. I should put x is equal to. So the couple of multiple angle ones just to get us warmed up. Now let's go back to the beginning, do our cosine and sine of a sum and difference. 105 degrees. This angle, 105, is on the 24 sector circle. 105 sits just beyond 90 degrees. So we're right up there. So that is not a multiple of 30 or 45. Actually, it's going to help to have this a little bigger, I think. All right, so we're right there. And what we're trying to do is come up with two angles that add to 105. You can do subtraction if you want to be creative, totally fine. But if we want to just get the basic skill down, we're looking for two angles that add to that. And I've mentioned several times that the easiest angle to deal with is 45 degrees because sine and cosine are both root 2 over 2, and that just keeps it a little simpler. So to back off 45 degrees, I've got to back off 3 of these 15-degree sectors. So if I back off 3 steps, 3 sectors, that'll be 45 degrees. So that tells me that 45 plus whatever that is will work, and that is 60 degrees. And those angles are known. They're multiples of 30 and 45, which makes them easy to compute. So we're going to rewrite this. Sine of 105 is sine of 60 plus 45. And we just plow through it. So first factor of the first term, sine 60, and then cosine of the second, plus or minus? Plus. And then we fill in the 2 blanks. Our 60-degree column, we already use sine, now we use cosine. Our 45-degree column, we use cosine, now we use sine. Sine of 60 is root 3 over 2. And then cosine of 45 is root 2 over 2. Cosine of 60 is 1/2. And then sine of 45, root 2 over 2. So if we simplify this, we get root 6 plus root 2 all divided by 4. That will be our sine of 105. And if you've done enough of these, you knew that that's the answer you were supposed to get. Because sine is the long leg. So right there, sine is the long leg, and cosine is the short leg. And if you've done enough of these, you know that the long leg is root 6 plus root 2 over 4. And what's the short leg? Root 6 minus root 2 over 4. And now in this case, we'd have to multiply it by minus 1 because we're in quadrant 2. So we kind of know what we should know what we're supposed to get. So if we do cosine of 105, we'll bust it into cosine of 60 plus 45. And we get cosine, cosine, plus or minus? Minus sine, sine. Let's just keep going this way. Cosine of 60 degrees is 1/2. Cosine of 45 is root 2 over 2. Sine of 60 is root 3 over 2. And then root 2 over 2. So this gives us root 2 minus root 6 over 4. And you can leave it like that. That's 100% correct. If you want to illustrate the geometry, you would factor the minus all the way to the front. So it's not in the numerator at all. And then you can see that it's minus 1 times the length of the short leg. But you can absolutely leave it like this first one. Totally fine. Either one of those. If you factor that minus out, make sure it's all the way in front. Don't have it tipping over the edge of the fraction bar. It's got to be all the way out in front. Okay. Now, When you have radians in these things, it can be a little complicated to try to stick with radians. Now, this is a case where you could convert to degrees because your final answer is numbers. Your final answer is not angles. So it doesn't really matter. If you switch to degrees and do it all in degrees, your final answer is numbers. You don't have any angle issue. So it's totally up to you what you do. 24 sector circle again. 11 pi over 12 is right there. 12 pi over 12 would be a pi. So I'm going to do it in radians, but if you wanted to switch that to degrees, how many degrees would that be? 165, exactly. And again, I think it's easiest to back off 45 degrees or pi over 4 radians. So that's 3 of these sectors. So that is pi over 4. And then we would need to figure out what that angle is in radians right there. And that angle is how many radians? Did you say 4 pi over 3? So if we count by pi over 3, we just have to be careful. Pi over 3 is 2 of these 15-degree ones. 1 pi, oops, I'm sorry. That's a pi over 6. 2 of the 15s is a pi over 6. 2 of the 15s is 30 degrees. So there's 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, which is the same as 2 pi over 3. 2 pi over 3. That is our angle right there. 2 pi over 3. 2/3 of the way to pi. So if we stick in radians, let's do sine of 11 pi over 4. So sine of 2 pi over 3 plus pi over 4. That's going to be sine of 2 pi over 3 cosine pi over 4. Sine same, so plus. Fill in the blanks for the 2 pi over 3 column and the pi over 4 column. We've got that. Any question on the setup there? Mm-hmm.
Would it make a difference if we started with the sine, the first sine, and it was pi over 4? So we put pi over 4 there instead of...
So if you wrote it as pi over 4 plus 2 pi over 3,
Yeah.
think it would matter? No, won't matter. Commutative law of addition, so will not matter. We'll get the same answer in the end. Yeah, good. Definitely good. Yeah, that won't matter. All right, so now we just evaluate each of these and combine our like terms. And sine of 2 pi over 3, that's 60 degrees up there. Or I shouldn't say it's 60 degrees, but the sine is the same as if it were at 60 degrees. Sine is the long leg, so that's root 3 over 2. Cosine of pi over 4 is root 2 over 2. And then cosine of 2 pi over 3, so we're over there. That's going to be negative 1/2. It's the short leg, but negative. And then root 2 over 2. So we get root 6 minus root 2 over 4. Does that make sense? We just said a minute ago that this is the value of the short leg. And is that what we're really trying to find? If we look at our picture carefully, are we trying to find the length of the short leg? Yeah, we are, right? Sine is that y value. And that's positive, and it's the short one. So, yeah, that makes sense. And then there's the long leg right there. All right, I'll let you work. We don't need to go through cosine. Cosine would be identical. We would put a cosine there, and then we'd have cosine, cosine, sine, sine, and the plus would be a minus. All right, next. Double angles. So here's a pretty typical problem where we're given information about a single angle, and we need to find this information about double angles. So what we know is that to calculate sine of 2 theta, let's put that over here on the side. Sine of 2 theta is 2 times sine of 1 theta times cosine of 1 theta. So in order to calculate sine of 2 theta, we need to know both sine and cosine of 1 theta. So that's the first step. We need to figure out, okay, we know sine of theta, but we don't know cosine of theta. So we're going to have to find that. And then cosine of 2 theta is going to be cosine squared theta minus sine squared theta. So these identities you definitely need to know. So you need to know your sum and difference identities for sine and cosine, the ones we just did. You have to know your double angle identities for sine and cosine. So those guys right there. Know those. If you somehow forget, you go to your sine and cosine of sum and difference. Right, this is cosine of theta plus theta. That's sine of theta plus theta. So if you forgot the cosine one, you would go to cosine of theta plus theta and use your cosine of a sum. You distribute to the first angle, so that's cosine of theta. And then it's always cosine of the second angle. Sine is same, cosine is opposite. And then we're missing a sine and a sine. And so you get cosine squared minus sine squared. So if you forget, you can always just think about your cosine of theta plus theta. And if you think about sine of theta plus theta, that also works. We'll get to it. All right, so we're told sine of 1 theta is a fifth. We need to figure out cosine theta, though, if we're going to use those identities. So a couple of ways we could go. One is we could go super geometrically, and we could say sine is 1/5, and we're in quadrant 2. So we could draw quadrant 2, draw a terminal ray in quadrant 2, and then label a terminal point in quadrant 2. And we know that sine is, what? Is it x or y? Y. So we could do this. We could say that point has coordinates x unknown, y1, and put the radius to be 5 to that terminal point. So then the sine value is 1/5. We don't know the x, so we compute it using the Pythagorean theorem. We know that x squared plus 1 squared has to equal 5 squared. So x squared is going to be 25 minus 1. So x will be plus or minus the square root of 24. That's 4 times 6. So it's going to be 2 root 6. And plus or minus? Which one?
Minus.
Minus, because we're in quadrant 2, where x is minus. Where x is negative. So now we know what cosine is. So this tells us that cosine of 1 theta is negative 2 root 6 over 5. Right. Cosine is the x coordinate divided by the radius. X divided by r. X divided by the distance to the origin. So now we're golden. We've got sine of 1 theta. We've got cosine of 1 theta. We've got our two identities. Now we just plug and chug. So sine of 2 theta will be 2 times sine of 1 theta, we said was 1/5. Cosine of 1 theta is minus 2 root 6 over 5. If you write it the way I just wrote it, make sure that negative sign is tucked up there in the numerator so it doesn't look like you're subtracting. And then our final answer here, we will get 2 times negative 2, so that's negative 4 square root 6, all divided by 25. That would be our answer for sine of 2 theta. Cosine of 2 theta is cosine squared minus sine squared, so we're going to take cosine squared and then subtract off sine squared. So in that first fraction, we have to square everything. So that's going to be 4 times 6 in the numerator, squaring the negative 2, squaring the root 6, and in the denominator, we have 25. In the second fraction, we get 1 over 25. So that'll be 24 minus 1, which is 23 over 25. Will be cosine of 2 theta. So these identities you definitely have to know. Tangent of 2 theta, you don't have to memorize any formula or be able to calculate any formula because you know that tangent is sine over cosine. So you know that you just divide these two. And if you're dividing by a fraction, you multiply by its reciprocal. So that's how I would prefer you to do tangent. Instead of memorizing or working with a new formula, work with a formula that you're already familiar with. Oops. Part of my answer vanished. What was that? Negative 4 root 6 over 23. There we go. All right. What quadrant is 2 theta in? 2 theta is in a different quadrant than theta, most likely. And what quadrant is 2 theta in? Which one?
3.
I hear a 3. So in quadrant 3 is cosine positive?
4.
4?
Yeah.
Everyone agree? Quadrant 4? So the cosine of this angle is positive, so we're on the right. The sine of this angle is negative, so we're on the bottom. Tangent is negative, so we're also on the right with that one. But these two is enough right there. All right, so we're in quadrant 4. Because cosine is positive and sine is negative. Quadrant 4. All right, you guys try this one. All right, try that one. Same idea, slightly different supposition. Same basic procedure. Those are our two identities that we have to use. Raise a wing if you need help. tangent is going to be equal to 8. That means y over x has to be 8. We're in quadrant 3 where x and y are both negative. So negative 8 divided by negative 1. So that should be where you're at. Does that choice of an ordered pair work for you? Does that make sense? You want y over x to be negative, y over x to be positive 8. And you're in quadrant 3. So that would be a great picture. And you should end up with an r value of root 65 when all is said and done. Use the Pythagorean theorem. X squared plus y squared will equal your r squared. So you square the negative 1, you square the negative 8. So that's all the preliminary work. The preliminary work is getting your ordered pair, getting your R value, because you need 3 numbers, x, y, and r. You need those 3 if you're going to calculate sine, cosine of theta. So what is sine of theta then? Sine of 1 theta. We have x, we have y, and we have r. So sine is which one? Sine will be square root of 65 under negative 8. Right, because it's the y value. Sine is the y coordinate. So it's the y coordinate, which is negative 8, and square root of 65 down below. And then cosine is negative 1 over square root of 65. Square root of 65 under negative 1. I don't know if I would say it that way, though.
Do we change it back? Do we change it around?
Rationalize the denominator? Yeah, you can do that. You don't have to right now. We can do it at the end. All right. So sine of 2 theta is 2 times negative 8 over square root of 65. If you're going to write it without parentheses, then make sure that negative is tucked up nice and neatly in the numerator. And when you multiply all this out, you'll get 2 times 8, which is 16, over 65. Oh, the square roots disappeared. Nice. So we get that.
So it would do the same. We rationalize the denominators.
Oh, you'll get the same answer. It's going to be a lot more work, though.
So it'd be better just to leave it like
Better
that.
not to rationalize until the end where you have to. Yeah. Yeah. Delay. Sometimes delaying is good. So now we're going to do cosine squared minus sine squared. Oh, good. Denominators, the square roots also disappear. We'll have 1 over 65 minus 64 over 65. So we end up with minus 63 over 65. What quadrant is 2 theta in?
1,
2. 2, quadrant 2, cosine is negative and sine is positive. So quadrant 2. And then tangent of 2 theta. Don't go dealing with some other identity. Just use sine over cosine. Sine. Dividing by cosine means multiplying by the reciprocal. So we end up with negative 16. The 65s cancel over 63. And that will simplify a little bit further. 4 goes into both of those, I believe. No. No, never mind. 4 does not go into an odd number. No. Not possible. 4 does not go into there. So that's simplified.
A for F.
Yes. Always try to reduce. Sometimes you can't. And we concluded that 2 theta is an angle that's living in quadrant 2. And that tangent value also confirms tangents are negative in quadrant 2. So that kind of fits in with the other 2 results. Okay. Definitely make sure you can do a problem like that. That's a very common problem on trig tests. Half angle identities. Should we take a break first? Half angle identities seem to be twice as hard. So let's take a break. We'll take a break. These ones I will generously provide to you for a small fee. Come to the exam. Come to the exam, and you shall be provided. What's that? I know. I went to a workshop once where there's this teacher that was giving a workshop on something like that. You could go up and basically buy. You would pay for it with points off your exam. So for 3 points, if you forgot some identity, you would come up and pay 3 points and you get the identity that you were missing. That's kind of funny. All right, so with the half angles, we are trying to calculate exact trigonometric function values for angles that are half of angles that we know. All right, so angles that are half of angles that we know. And let's do a couple examples of this. So sine of 112.5. We can't use a double angle identity to get to that thing, because for a double angle identity to work, we would have to know the angle that's actually half of that. To use a half angle identity, we have to know the angle that's double it. So it's a little counterintuitive, but when you look up at your identities here, you know that one. That's the one you know, because you can calculate it in there. So you have to know an angle that's twice as big as this. So for the half angle identity to work on a particular angle, you need to know the trig values for twice that angle, for double that angle. All right, so let's take a look. So sine of 112.5, 112.5 is in what quadrant? 2. Is sine positive or negative in quadrant 2? Positive. So we know we're choosing the positive square root of 1 minus cosine of twice that angle, 225, all divided by 2 inside the square root. And 225, if we go look at a unit circle, 225 is right here. There's our terminal point at 225 degrees. And cosine of 225 is what? Exactly. So 1 minus negative root 2 over 2. So that's going to change the sign in there. So I end up with that. Now we multiply every single term within the square root by 2. If we multiply every single term in there by 2, we get that. And then our final answer, I'm going to move this guy just a little bit out of the way. Right there. So then our final answer here, we can simplify the denominator. The square root of 4 is 2. So there's our final answer for sine. Cosine looks darn similar. Now you told me we were in quadrant 2. Should we choose positive or should we choose negative for the cosine value of 112.5? Negative, because we're in quadrant 2. Yes. And then this will be 1 plus cosine of 2 1/4. Minus, we evaluate, so that's going to be 1. Let's see. So cosine of 225. Oh, that's the same as sine of 225. Negative root 2 over 2. So we're going to have 1 minus root 2 over 2. And then the simplification procedure is identical. Multiply everything on the inside by a 2. So multiply that by 2, multiply that by 2, multiply that by 2. Look at that. We're almost there. One more step. One more step. And that one last step is just to reduce the denominator. So we have minus the square root of 2 minus root 2, and then all over 2. All right. Tangent.
I got a question.
Yeah, go for it.
How do you simplify the denominator? You just,
So if you have a square root, if you have the square root of a fraction, it's equal to the square root of the numerator divided by the square root of the denominator. So this fraction right here is inside the square root, so it simplifies to square root of the numerator over square root of the denominator, and the square root of 4 is 2. So we're essentially distributing the square root to the numerator and denominator. Make sense? And then tangent. Again, don't go remember another formula. Just use sine over cosine. Keep it simple. So we'll do sine divided by cosine, which means multiplied by the reciprocal. So we get that. And for these tangent ones, it's totally fine not to rationalize. Just these ones can be pretty tricky to rationalize. Don't bother to rationalize the tangent one if you come up with something like that. And did I drop a minus? I dropped a minus. There should be a minus out in front here.
Can you scroll up just quickly back?
Sure.
to
Yeah, yeah, absolutely.
So that's what it is. Cool. Thank you.
Yeah. So if we wanted to, we could use one of these that doesn't have the roots in it, and it would look a little simpler. We could definitely do that. But if we're trying to be efficient, we need to know tangent. Just do sine over cosine. All right. All right, you guys try this one. 165. So for the half angle to work with 165, we need to know the double of 165. We need to know the trig values for twice 165.
So do you times it by 2?
That's how I would double it? Yes. Absolutely. What were you doing?
Pretty much just guessing.
Oh, yeah, yeah. So with the half angle identity, the angle on the right is always double the angle on the left. Okay. So the half angle identities will only work if when we double that angle on the left, we get something we know. Okay. Something that's a multiple of 30 or 45.
It would only work if we can.
Yeah. If we get something that's a multiple of 30 or a multiple of 45. Okay. Yeah. Yes. This should be positive, though. Sign is positive in quadrant 2. Oh, this one of the, it's one. This is a negative. Cosine of 225 is negative. So it's a negative. Mm-hmm.
So for the sine equation, that's how I answer it.
Yep. Yep. Sin is negative.
It's a good way to remember it.
That's how I remember it.
Really obscure way to
With these trig identities, you've got to come up with crazy things.
Well, I was in one of the study rooms yesterday with my buddy Tim. And his dad used to teach math here.
Oh, Keely?
Yeah. So we were just like cranking out problems and we were writing sin everywhere.
Yeah.
No, it's bad.
Sin is good in math. Oh yeah, I know Jeff very well. His dad.
He's that's a cool guy.
Yeah.
I was over there building Tim's computer. It was just 20 questions and we were all building.
Yeah.
What's this do?
You go through the backyard. Does he still have the backyard filled with hops?
Oh yeah.
Yeah, I used to brew beer, and so he gave me 2 rhizomes 10 years ago that I used for years. And they're still growing in my backyard.
So we switched this on the denominator?
No, just one.
Well then, we switched it, and I'm confused. Because this is switched, and this is switched. So we switched it
So,
for both?
no, so,
I'm sorry.
no, that's fine. So that's the numerator.
Okay.
That's all positive.
Okay.
And then we're going to take the
that,
reciprocal of the denominator.
And then,
So we can put that sign whichever part we want. If
Okay.
that sign is out in front, so it can go here or here. And so when I flipped it over, I just put it
and put it
with
there.
the 2.
Okay,
Yeah.
that makes sense.
Yeah. All right, let's go through these guys. So first I just wrote them up there based on the identity. I haven't really thought about whether it should be positive or negative. What quadrant is 165 in?
No, yeah, dude.
Two. Second quadrant, 165. So the sign, is it going to be positive or negative? Positive, and the cosine will be negative. Yeah, good. All right, so again, for us to use a half angle to calculate with 165, we need to know twice 165. That's what shows up on the right. That's 330. So if we go to a 12-sector circle, 330 degrees is way over there. 330 degrees. And let's start our evaluation. So in the numerator here, we're going to have 1 minus cosine of 330 That's the long leg on that 12-sector circle, so that's minus root 3 over 2. And that's divided by 2. And now we're in that funky simplification process where we multiply every term inside that radical by 2. And that allows us to simplify into the following expression. The numerator will be square root of 2 minus root 3. The denominator will be 2. So that's cos of 165. Excuse me, that's sine of 165. Sine of 165. And then cos of 165, very similar. We'll have 1 plus cosine of 330. Oh, same. Yeah, root 3 over 2. Root 3 over 2. And our simplification process is very similar. We multiply everything inside by 2. And then we have to take the square root of the numerator and divide it by the square root of the denominator. The square root of the denominator is 2. So there's sine and cosine. And for tangent, we do sine over cosine. Dividing by that's the same as multiplying by its reciprocal, and I'm going to stick the negative with the 2. It has to be with one or the other, not both. So we'll put it with the numerator, since that makes more sense. Then we end up with this crazy fraction, and we just leave it as it is. That's too crazy to work with. You could do it, but you won't.
So how come the negative stayed all the way through with sine 165, but like in the other one, it went negative and then to a positive?
Where did it go negative to positive? In this line or the line below it?
In the first.
Oh, up above?
Yeah.
Two negatives make a positive.
So that negative there, you're talking about the leading negative, or are you talking about inside here?
Inside.
Oh, inside.
Yeah.
Okay, so right here, cosine of 225 is negative root 2 over 2. So it's minus root 2 over 2, which makes that a positive.
Yeah.
And then, yeah, but this one cosine is positive, so we don't have that situation. Okay. All right, half angles, I'll give them to you. Verifying identities. Everyone's favorite part. I'll do one, and then you guys can work on the second one. So let me just remind you that we don't know about that equal sign. We're trying to prove that that equal sign is legitimate. So we can't treat it like an equation. We can't do something to both sides. It's a little hard to read. That's secant squared of theta minus 1 over secant squared of theta. Okay. So you pick one side and you try to get to the other. I use LHS to represent the left-hand side, RHS to represent the right-hand side, and I like to stack it. That way I don't start making mistakes. I don't have a lot of space here, so I will go side to side. You just have to remember, if you're going side to side, don't all of a sudden stop and think you have an equation. Just keep on going. One direction valve. Keep going that way. Okay. You could use identities here that are Pythagorean in nature. But knowing that we need to get to sines, I'm thinking to myself, let's just simplify this by not dealing with secants. Let's go to cosines. So we're gonna write this as 1 over cosine squared of theta minus 1, all divided by 1 over cosine squared of theta. Now to clear the fractions, we have a fraction in the top, a fraction in the bottom. We can do what we just did with that square root thing. We can multiply each term by cosine squared. So if I multiply this top left term by cosine squared, I get 1. If I multiply that term by cosine squared, I get minus cosine squared of theta. And if I multiply that term by cosine squared, I get 1. So we're going to multiply everything by cosine squared of theta. Is that okay? Multiply each of those by cosine squared of theta. Now we're pretty darn close to the end. So that's going to be 1 minus cosine squared of theta, and 1 minus cosine squared of theta is sine squared of theta. Exactly. And that's the right-hand side. So putting the LHS and the RHS, that sort of helps to clarify that it's just a stream, and that the left-hand side is manipulated into the right-hand side. One common mistake is just to sort of jump out at some point with that equal sign and say, oh, I'll add cosine squared to both sides, or something like that. Just remember that you're going one direction if you're not stacking it. All right, so you guys tried this one. Sometimes these identities you can cut to the chase really fast sometimes. The typical advice is to start with the more complicated side. So which side do you start with? Yeah, start with that right-hand side. And then what? You have two fractions. What do you do with two fractions? How do you combine fractions? The denominators. You want to set the you want to make the denominators equal. Yes. So if you have two fractions and you want to add them, you got to force those denominators to be the same. So if this was 1/2 plus 1/3, what would you do? Yeah, exactly. Multiply this one by 3 over 3. Multiply this one by 2 over 2, and you'd be good to go. So same idea. It's just that you have trig functions. But it's the exact same concept. So we'll start with the right-hand side. I'll give myself a little bit of space. So what are we multiplying the first one by, top and bottom?
1 plus sine theta.
Yep, 1 plus sine theta. 1 plus sine theta over 1 plus sine theta. And this one we're multiplying top and bottom by 1 minus sine theta. Yeah, so those denominators, mathematically we call them relatively prime. So we multiply them together to get the LCD, the least common denominator. So I'm going to just combine the numerators. The numerator on the left is 1 plus sine theta. The numerator on the right is 1 minus sine theta. The common denominator is 1 plus sine times 1 minus sine, and that multiplies together to 1 minus sine squared. And what happens in the numerator?
Just turns into 1. 2, sorry.
Yep, 1 plus 1. Ooh, we like that. And then how about the denominator? Cosine squared, right? 1 minus sine squared is cosine squared. And then 1 divided by cosine squared is secant squared, which is the left-hand side. Cruising. Cruising. Hopefully not into a brick wall. Okay. Good question. So the denominator that we're generating is the product of these two. So we have, I'll just write it with an S, save some space here. So do you agree that that's the common denominator? Okay, so when we FOIL this out, first is 1, outer is minus sine, inner is plus sine, and last is minus sine squared. So the inner and the outer combine to 0. And so that leaves us with just 1 minus sine squared. That makes sense to everybody? So that's that difference of squares stuff from algebra. Any other questions on any step? Very suspicious. All right, good job. Definitely practice, because it's the only way to get these down. We'll do 2 more. Which one do you want to do? I'll do one. You guys do one. Let's see. I'll go through the top one. This next one is an important one. I want to make sure you guys, I see you practice that one. So I'll do this top one. We'll do it together. Which side do you want to pick, left or right? Left? Left's got secants and tangents. That's more complicated than sines and cosines, so let's just go with that. With this one, it's actually not going to be too much different either way. If you chose the right-hand side first, what do you think you would do to what do you think you would do for your first step? Yes. Yeah, if you chose the right side, you would multiply top and bottom by the conjugate of the denominator. Multiply top and bottom by 1 plus sine theta. Yeah. All right, so here, I'm going to switch to sines and cosines. That. We've got the same denominator already. That makes it pretty easy. And now here, it's going to be very similar to what we just talked about. We'll multiply top and bottom by the conjugate of the numerator. And when we multiply by the conjugate of the numerator, in the numerator we end up with 1 minus sine squared. In the denominator, I'm not going to multiply these together. Let's leave it as a product of 2 expressions. So that numerator is the same as the last problem. We had 1 plus sine times 1 minus sine. When you FOIL that together, the inner and the outer cancel to no middle term. All right, what's 1 minus sine squared? Yes, cosine squared. Want to be able to recognize that instantly. And then 1 factor of cosine cancels. And that is, whoops, I said 1 factor of cosine and I canceled 2 factors of cosine. 1 factor remains, and that is the right-hand side. All right. Any question on any stuff there? go with this one. You guys try this one. That left side is cotangent squared, if that's not, I'll rewrite it down here. That's cotangent squared up top. Divided by 1 plus cosecant of theta.
See if you can
Unravel that guy.
Yeah, that's an idea.
Cosine over that. Cosine over 1 minus sine. Cosine over 1 minus sine. So, cosine over 1 minus sine. Cosine squared. Yes. Look at that. So we went from cosine of 1 minus sine to 1 plus sine of cosine. Yeehaw! All right, what do you want to do first up here after we've chosen the left-hand side, because that definitely looks more complicated? Okay, turns things into sines and cosines. Always a great way to go. Turning things into sines and cosines is rarely a bad thing. So that's going to be cosine squared of theta over sine squared of theta in the numerator. And in the denominator, it's 1 plus 1 over sine of theta. Great. Okay, now we have a complex fraction, a fraction of fractions. So let's clear that. When we look at this, we should be seeing 3 fractions. We have this fraction, and that fraction. And what is the LCD between those fractions? Sine squared of theta. Right? That's the LCD. So we're going to multiply all 3 fractions by sine squared of theta. If you multiply all 3 by the same expression, you've preserved your equality. So in the numerator, cosine squared over sine squared times sine squared is cosine squared. That's the whole point. You're clearing out the fractions. And then downtown, when we multiply 1 by sine squared, we get sine squared. When we multiply sine squared by 1 over sine, we end up with just sine. We have that. All right, we're getting close. All right. Now the final answer has just sines in it. That numerator has cosines, and we can convert cosine squared into sines pretty easily. Cosine squared becomes 1 minus sine squared of theta. All right, and down below, can't we factor out 1 sine there? Factor out sine of theta, and then we have sine theta plus 1, which I could write as 1 plus sine theta. Doesn't really matter. That. Numerator factors. That's a difference of squares. Factors into 1 minus sine of theta times 1 plus sine of theta over that same denominator. And you see a common factor? It's written in a different order, but commutative law of addition applies. So this factor and this factor will cancel. And we're left with 1 minus sine theta in the numerator and sine theta in the denominator. And that is exactly the right-hand side. All right, so there's the whole thing. So any step in particular that you want to ask about?
It all look good.
All right. Let's get out of identities and into inverses. Inverses. These are a little bit more prescriptive, a little less nebulous. So with all these guys, the primary thing with inverses is to A, remember that you're dealing with angles. An inverse trig function is an angle. And we have to remember where they are. And let's see, do I have a summary? I can't remember if I added that into the gallery or not. I don't think I did. All right, so we have to remember what quadrant, or quadrants I should say, because there's going to be 2 quadrants for each. And when we look at our first one up there, inverse sine, which quadrants, which part of the circle? Inverse sine, top or right? Right-hand side. So inverse sine is an angle on the right. And we want to find the angle on the right that has a sine value of negative root 3 over 2. So 12-sector or 8-sector circle. 12-sector circle, let's put a couple of little tick marks there. And we know that we're dealing with this angle right there. And that's the one where the sine value is negative root 3 over 2. So that being said, that the only way we can get to that angle, we have to stay on the right and come down. And so what should that angle be? Negative pi over 3. Yep. Yeah, once these start to make sense, it's like, oh, yeah, I get it. All right, second one. Inverse cosine of negative 1, top or right? Top. Inverse cosine's on top. We want the cosine value on top of negative 1. Where's that? Right there? And that angle is pi. How about that one? Inverse tan of negative root 3. Top or right? Right-hand side. And 12-sector or 8-sector circle? 12-sector circle. And steep or less steep? Steep. Right there. That angle minus pi over 3. All right, let's go up to that guy. Inverse cosecant is related to inverse sine. Top or right? Right. Same as inverse sine. And we want the angle on the right with a cosecant value of negative 2, which is the same as a sine value of negative 1/2. So that tells us that we should be on the 12-sector circle. And we want that right there, I think. Do you agree? That will be the angle on the right with a sine value of negative 1/2. We could also use that identity. This is exactly that, which is negative pi over 6. inverse secant is related to inverse cotan. Top or right? Top. Looks like we're going to be dealing with a 8-sector circle. Put those two guys in. All right. So we are looking for an angle on top with a secant value of root 2. That's the same thing as looking for a cosine value of 1 over root 2, which rationalizes to root 2 over 2. So we're saying what angle on top has a cosine value of root 2 over 2? Yeah, pi over 4, right over there. Okay. Now, here's the one that's a little bit different. I mean, notice that inverse sine and inverse cosecant, both on the right. Inverse cosine, inverse secant, both on the top. And we've talked about the fact that 3 are going to be on top and 3 are going to be on the right. And so the inverse tan and the inverse cotan are slightly different. So inverse tan is on the right, but inverse cotan is on top. So that says find the angle on top with a cotangent value of root 3. All right, let's go quadrant 1, 12-sector circle. Angle on top with a cotangent value of root 3, which means the tangent value is 1 over root 3. 1 over root 3 rationalizes to root 3 over 3. So we're looking for the less steep slope. So that's going to be pi over 6. All right. Any one of those 6 cause you trouble? Any one of those 6 you want to talk about? Yeah?
Could you write down on the board one more example how you got like the pi over 3 is the cotangent of all the inverse?
This one here?
Yeah.
Yes. So, and you said pi over 3. Do you mean the root 3 or the...
Yeah, I'm just trying to like get the connection between the inverse and tangent.
Okay, got it. All right, so first off, inverse cotangent's on top. All right? And when we look at a 12-sector circle, if we look at the slopes over, we know we're in quadrant 1 because it's positive. So if we look at the ordered pairs here, this ordered pair is root 3 over 2, comma 1/2. This ordered pair here is 1/2 root 3 over 2. And if we find the slope of this one is y divided by x. And that's going to be 1 over root 3. And if we rationalize that denominator, it's going to be root 3 over 3. The steeper one here is going to have a slope of root 3. And that's the tangent value. So when we look at this, this is saying find the angle on the right with a cotangent value of root 3. And we know that tangent is the reciprocal of cotangent. So that's equivalent to saying find the angle on top with a tangent value of root 3 over 3. So then we look and we say, okay, which one has a tangent value of root 3 over 3? It's the one that has the less steep slope. It's going to be that one. That makes sense? So if we want the cotangent to be root 3, we want the tangent to be 1 over root 3. So if cotangent of some angle is root 3, that means the tangent of that angle is 1 over root 3. And when we rationalize that, we get root 3 over 3. Good? And that is the less steep terminal ray. Compositions. Compositions. All right. Talked a little bit about this at the beginning of the class. Sometimes when the two functions in the composition, when they're inverses of each other, sometimes they cancel. Sometimes they don't. In this case, do they cancel? Yes. We hear a yes and a no. Excellent. Excellent. That means learning is about to take place. All right. The outside function is the inverse trig function. So that means the final answer should be a ratio or an angle. Angle. The final answer should be an angle. Right? Inverse trig functions are angles. Trig functions are ratios. So the end answer should be an angle. All right. Inverse cosine lives on what part of the circle? Top. Inverse cosine lives on the top half of the circle. Is 7 pi over 6 on the top half of the circle? No. 7 pi over 6 is not on the top half of the circle. 7 pi over 6 is right there. So that's, bless you. So it's definitely not going to just cancel in this case. So let's just evaluate. Cosine of 7 pi over 6. X coordinate, 12 sector circle right there. What's that? Negative root 3 over 2. And now the question becomes, what's the angle on top with a cosine of negative root 3 over 2? Yeah, it's going to be that angle right there. It's going to be 5 pi over 6. Okay, so in this case, it does not cancel because the outer function is an angle, and the inner angle is not in its range. The range of inverse cosine, bless you, is on top. Ah, yes. Hard ones. Obviously, we have no clue what that angle is. Inverse tangent of t minus 1 over t, we have no idea. But we can come up with some algebraic expression for it. And let's see if that helps. So inverse tangent is on the right. It could be in quadrant 1, it could be in quadrant 4, it doesn't matter. We're somewhere on the right. I'm going to draw it in quadrant 4. Again, it doesn't matter. So I'm going to put that point right there. I'm trying to draw an angle that has a tangent value of t minus 1 over t. Tangent is y over x. So let's force a point on the terminal ray such that y divided by x is t minus 1 over t. And that's what I would choose. There's our radius. We don't know what that is. Is that okay? Inverse tangent of this ratio is the angle on the right that has a tangent value of t minus 1 over t. Tangent is y divided by x. So yeah, that ordered pair will generate a tangent value of t minus 1 over t. Find r. Let's find r. So r squared is equal to x coordinates squared plus y coordinates squared. So r squared is t squared. Let's see, foiling this out. Look at that. So that's 2t squared minus 2t plus 1. So r is the square root of that. All right. We now have an expression for x, y, and r, and we can answer the original question. The original question said, what is the secant of that angle? If you want to abbreviate it, let's just call that angle alpha. And we just drew a picture of alpha right here. What's the secant of that angle? Yeah, and cosine of this angle is t over r. So we have to form r over t. So our final answer will be square root 2t squared minus 2t plus 1 all divided by t. That will be our answer. So cosine is x over r. Secant is r over x. So we took our r expression and divided it by our x expression. There you have it. All right, you guys tried number 9. inverse cosine of t. Don't know what it is. Draw a picture. Whenever you're confused, draw a picture. Draw a picture.
I mean, it's better to multiply it out and combine the like terms, but I wouldn't dig for that. There's enough hard stuff on there. Yeah. There's other things to dig on.
Well, inverse cosine is in the top, so you can just pick. It's not going to matter. Yep. Yep. It'll turn out that it won't matter. Yep. So if I would just draw it in quadrant 1. Yeah. 1 over 2 will work, but quadrant 1 tends to be easier to work in, so go to quadrant 1. So the y value is unknown, so you've got to find that. Yeah. And what's your radius? So it's r. If your cosine value is going to be just t, you want x over r to be t. So if you choose x to be t, you're going to choose r to be t over the cosine is going to be x value, the r value. And if you've chosen the x value to be t, and you want t divided by the radius to be t, r has to be fix that. It'll come. Pick quadrant 1. Pick quadrant 1. Go with quadrant 1. When in doubt, go with 1. All right, so this is an angle on top. We can pick any quadrant we want. I'll just pick 1. We pick a terminal point. And we have 3 pieces of information. We have x, y, and r. This says we want the angle on top with a cosine value of t. So that means the x value divided by the radius has to be t. So if the x value divided by the radius has to be t, then we're going to force the radius to be 1. So that t divided by 1 is t. And the piece we don't know is the y value. So we use our Pythagorean theorem. T squared plus y squared will be 1. We're trying to solve for y. So we're going to get y being plus or minus the square root of t, plus or minus the square root of 1 minus t squared. Should we choose plus or should we choose minus? Plus. And now here's where you can confirm in your mind that it didn't matter if you picked quadrant 1 or 2. Because we're looking for the y value. If we drew this terminal ray in quadrant 2, we'd still be looking for the y value, and it doesn't matter. Y is positive in both quadrant 1 and quadrant 2. That's why it doesn't matter where you pick. Now we have all 3. We have x, y, and r expressions for each, x, y, and r. Now we can answer the question. The question said, what is the cosecant of this angle? Well, let's just call that angle alpha, so that's angle alpha. Cosecant of alpha is what? R over y, and our r value is 1, and our y value is that. Right, good. All right. Any questions on it? X, Y, and R. You need to know X, Y, and R. X, Y, and R. Okay. We only have 15 minutes, so let me do one of these two, because they're both very comparable. So look at the top one. Cosine of a difference. That's what you should be seeing. You know so well by now that inverse trig functions are angles, so you know so well by now, oh, that this is really just alpha minus beta. Right? Yeah, good. Okay, so cosine of alpha minus beta. We distribute to the first angle, cosine of the first angle, so it's cosine of inverse tangent of 3. The second factor is always cosine of the second angle. Cosine, cosine, cosine is opposite, so we're going to put a plus. And then it's going to be sine of the first angle. And then it's going to be sine of the second angle. All right, so that's applying the cosine of a difference formula. And we have two angles here. We have to deal with two angles. All right, we have two angles. They are not special. They're very not special. All right, so we're going to call the first one alpha and the second one beta. Genius. Okay, the first one, inverse tangent of 3. That's an angle on the right with a tangent value of 3. So I'm going to draw it right there, and I want the tangent value to be 3. So I'm doing this, and I don't know r. Right? That's on the right, and it has a tangent value of 3. Y divided by x is 3. We need to find r. So r squared will be 1 squared plus 3 squared. So r will be the square root of 10. That's the first angle. Second angle, inverse sine of negative 1/7. Inverse sine is on the right. And we have an angle with a sine value of negative 1/7. So we're going to draw this picture. If the sine value is negative 1/7, we're going to go negative 1 and 7 and leave the x value as unknown. Right? The sine is negative 1/7, so y over r has to be negative 1/7. Pythagorean theorem, x squared plus 1 equals 49. X squared equals 48. X will be the square root of 48. That's 16 times 3, so that's 4 root 3. Positive or negative? Positive. X is on the right. Now we can keep going here. So cosine of alpha. Cosine is 1 over r, so that's 1 over root 10. Cosine of beta. Cosine of beta is x over 7, so that's 4 root 3 over 7. Plus sine of alpha. Sine is 3 over root 10. And then sine of inverse sine. Oh, that's actually pretty easy because that's a cancellation one. The inverse trig is on the inside. So that's just going to be negative 1/7. You can also look at your picture and you get negative 1 over 7. So here we end up with 4 square root 3 minus 3 over 7 root 10 is the common denominator. And if you rationalize the denominator so that you don't have a square root in 2 places, we end up with 4 root 30 minus 3 root 10, all divided by 70. All right, so that's a longer one. Right, any questions on any one of those steps? If you're trying to evaluate an inverse trig function of a ratio that you don't know, draw a picture every time. Inverse trig function of an unknown ratio. By unknown, I mean it's not root 3 over 2, it's not square root of 2 over 2, it's not 1, it's not 0. If it's an uncommon ratio, draw a picture. Now let's go to trig equations. And let's try to solve a trig equation. That top one. Anytime we have a trig equation, like we talked about at the beginning of the class, we want a product of factors to equal 0. And right now, we can't factor this. There's two different trig functions. We can't unfoil this. So what do we do? What can we do with the sine squared so that we could get just one trig function in there? Yeah, change it to cosines. Exactly, good. So we're going to take this and make it 1 minus cosine squared. I'm just going to use a c because there's only one trig function here, so there's going to be no confusion. Sine squared is 1 minus cosine squared. All right, I'll distribute the 2. I'll collect the like terms. It's always easier to factor if the leading term is positive, so I'm going to multiply everything by -1. And we've got that. That we can unfoil. That is unfoilable. That's 2 cosine times cosine. Not a lot of choice with the 1s over there. Right? There's no other choice but this if it's factorable. If it's factorable. We have to check, make sure that's right. But that's the only choice. Because 1 can only be written as 1 times 1, and the middle term is negative, so we have to use a -1 and a -1. Let's check. That's +1. The outer is -2c, the inner is -c, so that's -3c, so good, it does work. This tells us that c, let's go back to cosine, is equal to 1/2, or cosine is equal to 1. 12-sector circle. Draw a little picture of our solutions. Cosine is 1/2 there and there. Cosine is 1 right there. Now this problem, we saw earlier today that if you have a quadrantal terminal point, you've got to be a little bit careful. And when we look back at our original equation, there's no cotangents or nothing that's going to be undefined. So we're going to be okay with that solution there. All right, so our answers then are theta equals pi over 3 plus 2 pi k. Or down here is 5 pi over 3 plus 2 pi k. And what about that one right there? How do we call that one? 2 pi k? Right. So that would be all solutions right there. And if we went 0 to 2 pi only, there we would get just the solutions that we see. So if we go just 0 to 2 pi, we're going to have 0. That's not 2 pi, that's 0. And I'm going to go in order this time. Pi over 3 and 5 pi over 3. All right, so all solutions and restricted solutions. Let's do, let's see what's on the next slide. I want to do, I want to do one more multiple angle one. So I'm going to do number 5. Before I post the notes, I'll just finish off the other ones and put them all up there so you have solutions to them. But let's do one more multiple angle one. Let's do that one before we vanish for 48 hours Bless you. All right, cosine of 4 theta is negative root 3 over 2. We're going to go to a 12-sector circle. And that 12-sector circle is going to have solutions that are in, let's see, cosine is negative. Cosine is negative root 3 over 2 at those two locations. So this tells us that our angle for theta is equal to 5 pi over 6 plus 2 pi k, or 7 pi over 6 plus 2 pi k. That's what 4 theta is equal to. How about theta? What do we do to get theta? Divide by 4. So that's going to be 5 pi over 24. And just remember to divide everything on the right by that 4. So 2 pi divided by 4 is pi over 2. So this is all solutions. That is all solutions. And then the last thing, let's go just 0 to 2 pi. How many solutions should we have? 8 solutions. We're going to have 4 from each group. So 5 pi over 24. I need to rewrite this so that the denominator is the same. So it's going to be 12 pi over 24. That's the same as pi over 2. That's how you would get a common denominator of 24. So what are we adding to the numerator? Adding to the 5, we're going to add a 12. So 5 plus 12 is 17 pi over 24. Add 12 again, and that's 29 pi over 24. Add 12 again, and that's 41 pi over 24. And if you were to add 12 another time, you'd be beyond 2 pi. So that's why you stopped with that one. Now we go to the next one. 7 pi over 24. And we start adding 12 to that. So then we're going to get 19 pi over 24. Add 12 to that. We get 31 pi over 24. Add 12 to that. We get 43 pi over 24. So those would be the answers that are between 0 and 2 pi. All right. Any questions on any of the steps for this guy? So not too hard. You just have to remember to divide by that coefficient. Make sure you divide that coefficient into both parts. And you're good to go. All right, I'll put solutions to these other ones up before I upload them. And good luck studying. Jessica's going to be available for hours and hours for math detention. Math detention. Have you earned math detention?